Let me now introduce our next speaker. Dr. Peter Wadhams is Emeritus Professor at Cambridge University. His work focuses on sea ice properties and thickness, including submarine voyages to the Arctic, and on the validation of satellite passive microwave data. To tell us more about it, let's welcome Professor Wadhams.
It's a great pleasure to be here and to be invited to speak at this memorable event for Joey, who is an old friend, and I wish him a very happy birthday. And while I'm waiting for the pictures to come up, also to say hi to Manfred, whom we worked with not a long time ago, but quite a while ago, with colleagues from the Arctic and Antarctic, including the first winter cruise in the Antarctic and the Winter Weddell Sea project back in 1986. And it's interesting that Manfred has chosen to say that it's the polar regions affect mid-latitude climate, because that's something that's been recently discovered and is very important, that the change in it looks like it's the change in the jet stream is resulting in alternating hot and cold conditions around the world, which is giving these very bad weather events which affect crop production in mid-latitudes like Cyprus. Fine. Okay, so now to go back to some of the work that was reported early on in this symposium by Claire Parkinson, Rob Masson, and Arnold Gordon concerning sea ice. And I'd like to draw attention to Joey's role. One of Joey's many roles as a scientist, was that not only did he derive the appropriate algorithms to convert signals, passive microwave signals, into ice properties, but he validated that and tested them against in the form of field work. So he was not purely generating algorithms and doing theory. He was out there on the ice, drilling holes, digging holes, and being a very, very active field researcher in establishing the validity of the algorithms that were being used. And so that's, I think, a part of his work which hasn't been advertised enough yet, and I think I'll just like to advertise it. So the topic is concerning ground truth and how it helps us to establish what remote sensing is telling us, so that we can interpret remote sensing data, whether it's aircraft data or satellite data, in terms of ice properties. So to do that, you have to have ground truth measurements. So every real development of an algorithm for use in remote sensing involves these two steps of doing the maths and the physics of what you think the algorithm should be, and then doing the field work to understand what ground truth is telling you about what's going on. So the ground truth is when we're thinking about ice properties is first of all telling us the thickness and the roughness of the ice. These are things which satellites can't give you directly, so you have to actually go out and measure thickness and measure roughness underneath the path of the aircraft or the satellite. The ground truth tells us flow size distributions with higher accuracy, and also other physical properties of the ice that we might consider to be important to know. And so this enables remote sensing data, which we're collecting at the same time, to be calibrated and interpreted. And okay, the aerial or satellite data tells us more about what type of ice there is present, and that's really one of the key reasons for doing remote sensing, is that it enables you to survey large areas of ice cover and say, this is first year ice or this is multi-year ice. So that's one of the key aspects of satellite remote sensing. But it will also tell you whether there's waves present, which is important again for getting at the role of waves in wave propagation affecting ice thickness, and in the spatial coherence of ice types, over what area does one particular ice type remain dominant. Also, if you do extensive validation of remote sensing data, say from a new instrument, then once you've done that, you can then use the remote sensing system by itself, and you don't need further validation. So let's look at what we're talking about here, and some extremely diverse types of sea ice. The first one is the backdrop to my slides. That's a typical present-day scene in the Arctic Ocean. And in the past, the Arctic Ocean was mainly covered with multi-year ice, but now it's almost entirely first-year ice. So when you stand on the ice, this is the kind of seascape that you see. It's very flat and boring looking. The ice itself is about 1.5 meters thick. It's less than a year old. And in this case, there's a refrozen lead in the middle of the scene, which is even thinner. So that's what you see over most of the Arctic now. And if you're in fast ice, in this case, the fast ice off northwest Greenland, near Karnak, and fast ice is thinner than it has ever been in the past. So it can be dangerously thin. And for instance, the Inuit hunters who use dog sledges have to be found that they tend to go through the ice, which can be fatal. So there's been an EU project where we've been fitting radar to the underside of their sledges, so that gives them a signal if the ice is too thin. It also provides data for the scientists. Now, this is the classic view of sea ice as it was in the 1970s, multi-year ice. That's ice which is many years old. Some of it partly melts in the summer to produce these Grand Canyon-like features, and then it freezes again in the winter. It's very, very difficult to walk over, and this was the big barrier to exploration and transport. But it isn't a barrier any longer because this type of ice has almost vanished. Now, Joey Comiso has been a leader in the discrimination of ice types and concentrations using algorithms derived from multi-frequency passive microwave. So to do that successfully, you need to do a lot of ground truth to establish what the different microwave frequencies mean in terms of the type of ice present. So I'll just go through, because of shortage of time, go through a very few questions that Joey's examined and that have been pretty vital to our knowledge of and understanding of how to do sea ice research. Firstly, there are places where there is pancake ice in large quantities, especially true of the Antarctic, where pancake ice is the ice type that's very dominant in the advancing ice edge in winter. But there's a pancake ice, there's a little zone of pancake ice in the Arctic, in the Greenland Sea, called the Odd and Ice Tongue, which Joey has worked on. It's a very interesting tongue of ice. On the left here you have the coast of Greenland, then you have the Arctic pack ice coming down southwards in the East Greenland Current, and you have a current which is driving out ice out into the middle of the Greenland Sea. This is called the Jan Mayen current, and the ice that forms in it is not Arctic ice as such. It's locally grown ice, and the ice that grows locally grows as pancake ice because there's so much wave energy present that it can't form a continuous sheet. So this is a dense field of pancake ice, and what happens with ice like that is that it rejects, as the ice forms, salt is rejected very rapidly because the ice is growing fast, and the rejection of salt back into the ocean increases the density of the surface water, and it tends to sink. So there's a little small area here where surface water is sinking, or was, and this was giving rise to a very extraordinary feature called chimneys, which were vertical cylinders, a bit like water going down a plug hole, but it was water gaining density, sinking down towards the ocean bed. And this formed part of the circulation of the Arctic Ocean, not the normal circulation, but the circulation driven by temperature and salinity variations, the AMOC. And these chimneys were extraordinary features, and we spent 3 years studying them, winter and summer. And unfortunately, this feature no longer exists. Because of climate warming, the Odd and Ice Tongue no longer forms, and you therefore don't get a rejection of salt into the ocean, allowing the formation of these chimneys. So we have a strange situation where one of the drivers of the AMOC circulation has stopped being a driver, and we don't really quite know what's going on, mainly because there hasn't been an opportunity to do fieldwork there. But while there was, and we were able to work with this pancake ice, it was one of the very interesting features of the Arctic ice. Here's another case that since sea ice multi-year ice has virtually vanished from the Arctic, one of the few places where there's substantial amounts left is just along the north coast of Greenland. And that would probably be the last final place where polar bears will survive. And here we see, again, the passive microwave showing the percentage of different ice types present, or concentrations of different ice types. And the purple here is multi-year ice coming out from the north of Greenland and coming a little way down the East Greenland coast. Now we move to the Antarctic, and there the situation is quite a lot simpler on the whole, because we're dealing almost entirely with first-year ice. And as previous speakers have pointed out, there's a huge difference in area between the ice in summer and the ice in winter. There's difference between 3 million and 19 million square kilometers. So this shows winter and summer extents. And the passive microwave shows details of how the ice properties change through the year. And this is from the NASA, the first NASA atlas. And we see that this is in a typical average year. We see the ice as we move towards spring, the ice retreating, and the beginnings of open water areas in the Ross Sea and the Weddell Sea. And here's the Ross Sea becoming open. Then we go up to the other 6 months and we find that the minimum ice extent is in January and February, then it starts to grow back again. So we can see very nicely the annual cycle of ice extent shown up by passive microwave and giving us a complete view of how the Arctic ice cover varies between winter and summer. And of course, this is on an average year, but of course, since data is collected continuously, you can look at particular years and see the differences. For instance, this is 4 successive Januaries, and the interesting thing there is that is the navigability of the Arctic in the summer, because in the summer the two interesting areas really are the Weddell Sea and the Ross Sea, and there's a big variability between the amount of open water that occurs in the Weddell Sea from year to year. For instance, Shackleton got caught in ice in the eastern Weddell Sea when he thought he was actually sailing far south, so he would have a nice start to getting to the South Pole. But you can see that it varies from being open like this to being absolutely closed. Similarly, the Ross Sea, which is normally open in the summer, and also there are many scientific bases around the coast of the Ross Sea, the Italian bases here, because ships can get in there in the summer and replenish the bases. But you can see that that doesn't apply to every summer. Here's a summer where the Ross Sea entrance was closed. So variability is the watchword here, and again, it's passive microwave gives us our best picture of how the ice conditions change. Now, this is working with passive microwave to track Arctic and Antarctic sea ice has been one of the things that Joey's worked on a lot. If we want to now do other kinds of ground truth, one of them is to try to distinguish the thickness of the ice or the roughness of the ice from surface data, and that can be used to interpret airborne data. So the thing I'm talking about here really is a scanning laser. This has been mentioned already as a standard instrument used in polar research. It's like a multi-beam sonar in the sense that it has many beams which give you build up a picture of the surface of the ice so that you can see, and this is achieved by a form of a rotating prism. And so you see where there's ridges and where there's thin ice. So here we have pressure ridges with the blue being the thinner, younger ice in between. Now that's the top surface, and so from an aircraft, the laser is telling us what's going on as far as surface roughness is concerned. But if you can combine that with data collected from underneath, then we really have a very nice method of validation. And this is an underneath view. This is obtained from a submarine. And here I've been very lucky, and in fact, in working with Joey, we've had a very nice kind of relationship in that submarines allow us to do a lot of ground truth about concerning ice thickness and roughness variations, which are now allow very good validation and calibration of airborne and satellite data. So there's been many experiments that Joey and I have done together involving an aircraft and a submarine. And the submarine has usually been a British submarine, because the British Ministry of Defence has been very helpful in allowing scientists to go on submarines and collect data and publish it. And the aircraft that's been used most in flying over the top has been the NASA P3, which was really well equipped with lasers, SAR, passive microwave. And so using the P3 to follow the same track as a submarine has been an invaluable source of data from joint experiments. So here we see the underside. This is a pressure ridge seen from a submarine. And so the typical collaboration experiments between NASA and ourselves has been one in which the aircraft has flown along the track of the submarine. And so submarines have tended to go up to the North Pole. The blue, here's a couple of tracks. The blue one shows a 2007 voyage, which went to the north of Greenland and ended up at Sedna, which was an ice camp in the Beaufort Sea. Then the red one was a voyage 4 years earlier to the North Pole, because they like to go to the North Pole. And both of these voyages have had the advantage that it's been possible to go outside the limited area that the US had taken on, called the Gore box. The Gore was concerned about submarines interfering with national sovereignty. I'm sure Trump wouldn't be so bothered, but in those days, national sovereignty was respected. And so a box defined the outer limits of where a US submarine could go. The British submarines had arrangements, I think, with Canada and Denmark. So we were able to go somewhat outside those limits, which meant being able to work close into the coast where there's very heavy ridging north of Greenland. So we have a history of about half a dozen, or more than that actually, submarine voyages to the North Pole, where I would go in the submarine and Joey would go in the aircraft. And so this was an early one in 1976. In fact, in this case, we were working with a Canadian aircraft. We hadn't started to work with the NASA aircraft. And here's the submarine at the North Pole, the Sovereign, with scientists and myself standing around amazed at how we got up through such thick ice. And initially, the data collected would be single beam upward looking sonar data, which is very good for giving thickness distribution of the ice and the roughness distribution of the ice and the distribution of the heights or the depths of individual pressure ridges. And here are some individual ridges, and we see different thicknesses of undeformed ice in between the ridges, including a thin ice in a refrozen lead. So this will be the first under ice data that we would work on in comparison with the airborne data obtained from the remote sensing aircraft. Is another narrower beam data set. Then we started to take more equipment on the submarine. First of all, we took a Sidescan sonar, which gives you a shadow picture of the underside and shows you where the ridges are. And so it gives you the shapes of the individual ice flows and the ridges, although it doesn't actually give you the depths of the ridges as such. But then from after that, we moved to multibeam sonar, and this was the ultimate that we managed to do so far, which is mounted a multibeam sonar on the bow dome of the submarine. And this is just the data coming out as seen from the control room. And we can see the submarine doing two parallel swaths, and with a pressure ridge that's coming across from one swath to the next. So we're able to do 3D mapping in high resolution of the underside roughness of the ice. So that was a real advance. And the problem is that two problems occur with this. One is that the resolution of the submarine data is not as good as the best that can be achieved, which is the use of an autonomous underwater vehicle, an AUV. So with an AUV, we use a multibeam sonar, and we run the vehicle much closer to the ice because there aren't any people in it, so you don't have to avoid the danger that you might hit the ice underside. So you can collect much better data this way. I'm sorry, I can't. Oh, I do. And to say I don't have all the slides that I would like to have because I've been locked down in Italy for the past few months, and all of my slides are in Cambridge. Anyway, let's look at another form of ground truth, which is the use of lasers. And here it was a classic case of a submarine versus the NASA P3. And this was done in 1987 with Joey, and it was a very big experiment, and with lots of different sensors involved, both on board the P3 in the form of satellite sensors and on board the submarine, so that there were many comparisons that could be done between different data sets. And so quite a lot of papers came out of this voyage. But one of the most interesting and unexpected is this graph here, where we have a set of overlapping probability density functions of ice thickness. Now, one of the functions is ice draft as measured by the submarine. And the other one is following exactly the same track, the ice elevation above, not above sea level, but above the level ice surface, measured by a laser. So if you put the laser distribution on top of the submarine distribution, they fit pretty much exactly, so long as the tracks were the same. So here's the 6 cases where the tracks were identical. The ones at the bottom, where the submarine and the aircraft parted company somewhat. But here they were close together, one on top of the other, and the fit is very exact. Exact, that is, so long as you multiply the elevations by 9, then you get it to match the drafts. And that multiplying factor is season dependent. So it's not quite as simple as it looked. It looked wonderful when we got this. We thought, well, we just multiply by this factor, and we can get from laser, from heights of the ice above water to the depths below water. But in fact, it turns out that this is something that depends on the season of the year, because in the winter, there's a lot of snow, and the laser is then affected by the snow thickness, which is less dense than ice, of course, but just as thick. So this is the voyage, and here we are at the North Pole. We were working with an American submarine, the Sea Devil, and here is our ship, the Superb. The interesting thing you might notice is that when the Royal Navy equips crew for polar voyages, they wear desert camouflage clothing. So that's something inexplicable. But the problem here is that all the wonderful data I was hoping to show you that came out of this voyage is unfortunately not available to me here because I'm in the wrong country just at the moment. But this was, in terms of surface validation, just exactly what is needed, and it's provided by the fact that you can match a submarine and an aircraft together. And this is something that Joey has worked on a lot, and I've worked on it with him. And I think this is one of the best ways of being able to validate ice data. And so we hope there'll be more of this done. Of course, there may well not be. It depends on who takes submarines to the pole and whether they take scientists in the future, and also whether we're the scientists or whether we're too old. So lots of things, unknowns there, but it would be really good to get more data of this kind. So it only remains to say happy birthday to Joey, and I hope we'll work together again a lot more in the future, because we've had some wonderful times working together in the past. And there's another little greeting from somebody else who knows you.
Hello, Joey. Yeah, hi. And I have wonderful memories of you and the other people on Paul Ashton in '86 in the Winter Weather Sea project. I was the writer of the book on Canadian Paul Ashton and learned so much. And you are really lifelong friends, and thank you very much, and best wishes from both of us.
Thank you.
So thank you very much, Professor Wadhams, for that very interesting talk.